let's continue learning about Riemann sums. And even though the section is called the Fundamental Theorem of Calculus, we're not actually going to get there quite yet. We need just a little more time, just this video. Next video, we'll learn about the Fundamental Theorem. Anyway, last time we learned about this stuff, but remember I said you didn't need this. I wanted you to see it, but I'll never ask you to do that on a test. Okay? Now, here is a very important term that you do need to know. The definite, it's an I, the definite integral of a function f from a to b is the net area under the curve, and it's defined to be, now this is some new notation here, that's an elongated s from a to b of f of x, and then we write dx, and really this equals, well, the same thing I have right here. Limit as n approaches infinity of the sum from I equals 1 to n of f of a plus I delta x, where, of course, delta x equals b minus a over n. Now, the textbook might be a little different. It might be technical about things. It might even use asterisks. I've seen some textbooks do that. Just go with this definition, okay? Just go with this. It's the easiest, okay? So if I say write this as a Riemann sum, I'm not asking you to solve it, don't worry. Just say write it as a Riemann sum. Well, we'd say, okay, delta x equals 8 minus 5 over n, which is 3 over n. And we know by definition that the integral of this guy equals the limit as n approaches infinity of the sum from 1 to n of, so what's it going to be? We know it's going to be f of a plus I delta x times delta x. Okay? And we can do a little bit better than this, right? This is almost maybe an 8 out of 10 right here, right? Maybe a 7 out of 10, I don't know. But instead of writing f of, we're actually going to plug this in. So we're going to get 5 times all this junk to the 6th minus 4. And then all of that is going to be times 3 over n, right? Do you see where we got this from? This right here became this right here. That right there became that right there. And maybe, I don't know if you can sort of make a connection. Maybe you could see that, like, this guy became sort of this guy, I don't know. Okay, maybe you could say, like, this guy is that guy. Maybe that guy's that guy. I don't know. Right. Okay, and we could go the other way, right? I could say, take this disgusting limit of a sum, whatever, write it as a definite integral. So what you have to do is you have to know that we can rewrite this as, as n approaches infinity, the sum from I equals 1 to n of, now this is e to the 1 plus, note that I could write this as I times 2 over n. That's very important. And then we're multiplying all this by 2 over n. So if you stop and think about it for 1 sec, what is delta x? I'll write this in red over here. Delta x equals 2 over n, right? We see it here and here, just like in the definition of the integral. Right. So now that we know that, we can say, okay, so maybe this is the same thing as well. Instead of all this limit of the sum nonsense, I don't do that. I just write the integral sign. Maybe I'll just write it down here. I'll just write this as the integral sign. And I guess I might notice that this right here is our a. So I guess we're going to be integrating from 1 to, well, hold on a second. If delta x is 2 over n, and delta x equals b minus a over n, then that implies that b equals 3. So we're integrating from 1 to 3 of, now what is this function? It's just going to be e to the x dx. And we write dx as instead of writing, delta x. It's just sort of a convention. So much nicer, wouldn't you agree? So this is why we use this notation in the first place. It's just better, right? It's just so much easier to write. Even though I know all of this is still kind of annoying and weird, different. Okay. Now, a couple of things. I stole this from Stewart, but this is also true in Neuhauser. I forget what page it's on in Neuhauser. These are just properties to know about the definite integral. If you swap the bounds, then you swap the sign. Integral from a to itself, or, of anything is 0. You can split the integral over sums. This is going to equal, I didn't write this one out, but it's the same way that derivatives work well with constants. Integrals work well with constants. And it turns out if you integrate from a to c, and then c to b, this is the integral from a to b. Okay. And that's all.